Okay, so the next topic is what we would call composite functions, which is kind of a combination of two functions. And in pre-calculus, it's not really obvious what the big deal is with composite functions. But if and when you get to calculus, you find out that composite functions are integral, no pun intended, to doing calculus. So there are a couple of ways of writing composite functions. But remember, when we have a function, just a function by itself, f of x, what do we say? We say f of x, or function. It's a function of the variable x. Okay, so that's what f of x means. So one way of doing this composite function is f of g of x, or you can put the f outside parentheses, and inside the parentheses is g of x, because normally in the parentheses we have x. So the function, this is a function of x. What this is saying is f is a function of g of x, where g is a function of x. Okay, so here's an example. Let's say f of s is s squared, g of x is x minus 3. So what you can do is you can substitute g of x into here in terms of the parentheses, but it also means that you can substitute this in for s. And ultimately, the composite function is a function of x. That's why I used s instead of just f of x is x squared. So the composite function f of g of x is the quantity of x minus 3 squared. And again, you might say, well, why didn't I just call f of x equal x minus 3 squared? And depending upon what you're using, how this is all put together, what the purpose is, that may be fine, just to call f of x that instead of using this composite function. So let's look at another example. So f of g of x, or f of g of x. So f of s is equal to the square root of s. So if I want it, and I have g of x is x squared minus 3x plus 4. So if I want f of g of x, instead of putting s, instead of having s as the argument, g of x is the argument. So this goes there, but it also goes, well, actually, this goes there, but that goes there. So f, the square root of s, where s is replaced with g of x, is the square root of x squared minus 3x plus 4. Now, what if we change the order of things? So let's say I said that f of s was x minus 3, and g of x was equal to x squared, and that should be s over here, not x. So I can do the same thing, but it's the opposite order. So in this case, f of g of x. I tend to use the second terminology, f of g of x. So again, what you're going to do is you're going to plug in g of x into here, and then instead of putting g of x here, I'm going to put the corresponding x thing. So for this particular example, f of g of x is going to be equal to x squared minus 3. So x squared is substituted for s. Let's look at this next one. How would we do that? Well, again, you would let f of s equal s squared minus 3s plus 4. G of x would be equal to the square root of x. So I plug that into here, so I get f of g of x. And then in the right hand side, for s, I put in the square root of x. So to get the square root of x, quantity squared minus 3 times the square root of x plus 4. and the square root of x squared is x. So I get x minus 3 square root of x plus 4. Okay, another one. Now, we haven't actually introduced the sine function, but you should know it from geometry. So again, what we're going to do is, for s in the argument, we're going to put g of x. For s in the function, we're going to put the sine of x. So it becomes 1 divided by s, but s is the sine of x. Okay, here we have f of x. Well, let's go back and do this one the other way, just so you, again, let's say that f of s was equal to the sine of s, and g of x is equal to 1 over x. So the composite function f of g of x equals the sine of 1 over x. Okay, here we have 1 over the square root of x. Actually, what I'm doing now is I'm switching to different notation because this is more typical. So before we had s here and s here, but what we're going to do is we're going to substitute for x, put in g of x, and for x here, we're going to plug in x cubed minus 4. So if you do that, you'll get 1 over the square root of not x, but the square root of x cubed minus 4. So again, let's just switch them. So let's say f of x is x cubed minus 4. G of x equals 1 over the square root of x. So f of g of x equals 1 over the square root of x quantity squared cubed minus 4. Obviously, you can see in most of these cases, f of g of x and g of f of x are not the same thing. There is a special case, which is the next section, where f of g of x and g of f of x are the same, and they're both equal to x. Okay, so that's the way you go about creating composite functions. The thing about a composite function is you've got the original two functions, which have domains of them, have their own domains, and then you combine them into a function. Now the composite function, let's say I call this h of x. So h of x is 1 over the square root of x cubed plus minus 4. The domain of this function, h of x, is going to be different than the domain of the composite function. And that's because you have to reflect the domain of the original functions into the domain of the composite function. So in this case, for the composite function, the domain, this is all real numbers, and you might think, well, the domain of the composite function is all real numbers, but the reality is that because of the limitation on the square root of x, as far as the domain has to be greater than 0, then this original function has to be this has to be greater than 0. So this x here has to be greater than 0. Therefore, when you put it in there to make the composite function, this domain has to be limited so that the function can be evaluated. So what we do, instead of saying it's all real numbers, we say that x cubed minus 4 has to be greater than 0, or x cubed has to be greater than 4, or x has to be greater than the square root of 3 over 4. So for the composite function, this f of g of x, the domain is that x is greater than or equal to the cube root of 4. So that domain of the composite function is neither the domain of the f of x or the g of x. Oh, it's poor English. So let's fix that. We have done the following. we've done f of g of x. Can we do g of f of x? Well, yeah, we just did that. Okay. So let's just look at a few more examples. So yeah, let's do both of these. So you know, we did. I guess we've already done this, didn't we? These are the same functions. So in this case, f of g of x was equal to, you plug that into there, so that became x minus 3 squared, whereas g of f of x, you go the other direction. You plug that into there, so that's x squared minus 3. Yeah, we already did that, so don't have to do that one, don't have to do that one, don't have to do that one. Is g of f of x equal to f of g of x? Always, never, sometimes, okay? Obviously, it's not always, because none of these actually have had that case, but could we say never? Well, we can't really say that, but we'll find out. There is a case where sometimes g of x and f of x, g of f of x and f of g of x are the same. Okay, so that's it for composite functions.